so I'll be talking about the biosynthesis of heme. As you all know, it's synthesized in the liver and the bone marrow. And also what you need to know is that the first step and then the last 3 steps occur in the mitochondria, while the rest of the steps occur in the cytoplasm. I actually had a really hard time remembering all this back then, but thank God for mnemonics. Anyway, so the whole story starts with a non-essential amino acid, glycine, which provides the nitrogen, and the citric acid cycle intermediate, succinyl-CoA, which provides the carbon. This is a very important step, by the way. It's the most important step, in fact. It's both the rate-limiting and committed step of the pathway, and it's important to remember that it requires PLP as a coenzyme. So basically, the glycine and the succinyl-CoA condense to form ALA by ALA synthase. The enzyme name is pretty easy. Here we're synthesizing ALA, so the enzyme is ALA synthase, obviously. So after this step occurred in the mitochondria, we shift to the cytoplasm. Here, 2 ALA molecules condense. 2 ALA molecules, they condense to form porphyroglinogen. Okay, so basically this occurs using the enzyme aminolevulinic acid, or ALA dehydratase. Now this enzyme is very unique because it contains zinc, and so it's sensitive to metal poisoning. For example, if someone had lead poisoning, then it would lead to the replacement of zinc by lead, and that would cause the inhibition of this enzyme. And as you all know, if an enzyme is inhibited, then its substrate accumulates. And why is that? Well, it's because the process can't go any further, and so the substrate keeps building up and keeps being synthesized in huge amounts with nowhere to go, because the enzyme involved in getting it going to the next step is inhibited. So in this case, ALA is what accumulates because of the defect in the enzyme ALA dehydratase. After that, 4 porphyroglinogen molecules condense to form hydroxymethylbilane through the enzyme porphyroglinogen deaminase, or another enzyme, or another name for this enzyme would be hydroxymethylbilane synthase. Now, the enzyme name is pretty straightforward. You synthesize hydroxymethylbilane, so obviously the name of the enzyme would be hydroxymethylbilane synthase. And this is the last of the linear intermediates, okay? So the linear intermediates stop here at the hydroxymethylbilane. Now, after that, we isomerize and cyclize this hydroxymethylbilane into uroporphyrogen 3 using uroporphyrogen 3 synthase. After that, decarboxylation of the acetate groups in this uroporphyrogen 3 occurs using the enzyme uroporphyrogen decarboxylase to give us coproporphyrogen 3. Now we go back to the mitochondria where the remaining steps occur. So basically, the coproporphyrogen 3, it enters the mitochondria and it gets decarboxylated by coproporphyrogen 3 oxidase and to form protoporphyrogen 4, which then gets oxidized through the action of protoporphyrogen oxidase to form protoporphyrin. Now, finally, this protoporphyrin will then form the final anticipated product, which is this heme, by the action of furanochetase. And by the way, this enzyme isn't really that important because the pathway would have occurred with or without it, since it is a spontaneous step. But this enzyme is what gets things going quickly, and it accelerates the step. Now, when this heme accumulates and we don't need any more heme, it will be converted to hemin by the oxidation of ferrous into ferric ions. And this would then exert negative feedback all the way back here on this enzyme in the very first step of this pathway, which is the ALA synthase. So this heme would exert negative feedback, and it would tell it to stop the pathway because we have enough heme. Now, basically, now for the porphyrias. Okay, we have two types, which are classified based on where the enzyme defect is found. So they can be either hepatic or erythropoietic, if they're found in the liver and the bone marrow, respectively. Now, there are two important things to look out for. The first one, which I've already mentioned, is that, for example, if we have a defect in an enzyme, then its substrate will accumulate because it basically has nowhere to go. The other thing is that if the enzyme defect occurs prior to the synthesis of these cyclic structures, which is like around here, using where the linear structures are at, then the symptoms exhibited would be mainly the abdominal and neuropsychiatric signs. However, if the enzyme defect occurs after the synthesis of cyclic structures, which is around here, then the individual would experience photosensitivity. But there is one exception to this. When we come to the congenital erythropoietic porphyria, which is here, which is due to a defect in the uroporphyrinogen 3 synthase, then we would get an excess of hydroxymethylbilane. But wait, didn't I say that it's a linear molecule and not cyclic? Then how come it causes photosensitivity? Well, it's because hydroxymethylbilane gets spontaneously converted into uroporphyrinogen 1 and coproporphyrinogen 1. And these both are cyclic structures and are what cause the photosensitivity. Now moving on to the mnemonics. There are mnemonics for the intermediates and for the diseases. For the intermediates, we have some, great, for succinyl-CoA and glycine, doctors for delta ALA, prescribed for porphyroblinogen, high for hydroxymethylbilane, unlimited for uroporphyrinogen 3, copious for coproporphyrinogen 3, precious for protoporphyrinogen 9, processed for protoporphyrin, and heme for heme. For the diseases, we have DAM for delta ALA dehydratase porphyria. She is acute for acute intermittent porphyria, CON for congenital erythropoietic porphyria, and she probably for porphyria cutanea tarda, has for hereditary coproporphyria, a variety for variegate porphyria, and of estate properties for erythropoietic porphyria. And that's it.